Every space movie you have ever watched taught you one lie. A field so packed with rock that pilots must dodge and weave just to survive crossing it. Real spacecraft have now flown through that exact region more than a dozen separate times, and not one of them has ever needed to dodge a single piece of debris. Somewhere between Mars and Jupiter drifts the wreckage of something that almost became whole. 2 centuries ago, astronomers were certain a 5th rocky planet belonged in that gap, and they organized a continent-wide search to find it. What they found instead was stranger and far more troubling than a missing world. Tonight, we go looking for whatever stopped a planet from being born, and why the movies still refuse to believe it. If this kind of quiet wandering feels like good company on a slow night, liking and subscribing greatly helps this small channel more than you know. Get comfortable now and let the night take over. In 3, 2, 1, liftoff. Picture the belt the way you have always pictured it. A churning field of boulders tumbling over one another in total darkness, packed so tightly together that a pilot has to bank and weave and hold his breath just to survive the crossing, each near miss closer than the last, each impact only barely avoided. It is one of the most familiar pictures in all of popular imagination, repeated in one adventure story after another for the better part of a century, so familiar by now that most people have never once stopped to ask whether it is actually true. It is also, point for point, close to the exact opposite of what is really sitting out there in the region of space between Mars and Jupiter. Real spacecraft have made that same crossing more than a dozen times now, and not one of them has ever had to dodge so much as a pebble to do it. They cross on quiet, carefully plotted courses, sometimes taking the better part of a year to get through, and on the other side, mission engineers report the same thing every time: nothing to report. No near misses, no white-knuckle course corrections, nothing but open dark and the occasional distant point of light drifting slowly past a window. Later in this video, we will put exact figures to just how much open space is genuinely out there. And those figures are stranger, and in their own way more unsettling than most people expect. But before we get to the numbers, it is worth sitting with a quieter question first. If the danger was never real, where did the idea come from in the first place? The answer did not begin in a movie studio, and it did not begin with special effects. It began with a working astronomer writing by lamplight in a house in northern Germany, in an age when the fastest way to send a letter across a country was still by horse, and the fastest way to send one across an ocean was still by sail. His name was Heinrich Wilhelm Olbers, and more than any other single person, he is the reason this misunderstanding exists at all. By profession, Olbers was a physician in the port city of Bremen, a careful, well-regarded doctor who spent his days seeing to the ordinary ailments of an ordinary city. But by night, once the last patient had been seen and sent home, he climbed to the upper floor of his own house, a level he had converted, piece by piece, into a private observatory, and there he remained until the sky began to lighten toward morning, tracking the movement of the stars the way other men of his era tended a small side business after supper. This kind of double life was not as unusual then as it might sound today. In an age before professional astronomy existed as a paid career at nearly any observatory outside a handful of royal courts, some of the era's finest sky watchers were doctors, lawyers, and merchants by daylight, people with steady incomes and quiet evenings who simply loved the discipline of watching the sky closely enough to notice when something in it had changed. Olbers happened to be one of the most gifted amateurs of his generation, and he had taken up the habit remarkably young. At just 21 years old, while sitting up through the night nursing a sick fellow student back to health. He passed the long hours working out an elegant new method for calculating the path of a comet from only a small handful of observed positions, a shortcut so useful that astronomers across Europe were still relying on his approach long after Olbers himself had died. He was born in 1758, and he would live to be 81 years old, and somewhere in the years between, this quiet Bremen physician would do more than almost anyone else alive to shape how people have pictured the space between Mars and Jupiter ever since. To understand what Olbers eventually found there, and why it convinced him something violent must have happened, it helps to go back a few decades earlier to a puzzle that had been quietly nagging at European astronomers for most of the 1700s. Passed between observatories the slow way, in letters that took weeks to cross a border and months to cross a sea. There is an odd piece of arithmetic worked out independently by two German astronomers named Johann Titius and Johann Bode that seem to predict roughly how far out from the Sun each planet in the solar system ought to sit. The trick is almost embarrassingly simple. Start with a small number, roughly double it at each step, add a fixed constant, and the resulting sequence lines up with almost eerie neatness against the known distances of Mercury, Venus, Earth, Mars, Jupiter, and Saturn, all 6 planets known to exist at the time. It was the kind of pattern that invites suspicion precisely because it works too well, and for decades, most serious astronomers treated it exactly that way, as a pleasant coincidence and nothing more, the sort of numerical curiosity a school teacher might use to entertain students, rather than a genuine scientific tool. Nobody had a good physical explanation for why the solar system should organize itself around a piece of arithmetic rather than any known law of nature, and without that explanation, the pattern remained a parlor trick, interesting to mention at a dinner table and useless for anything more. Then, in 1781, everything changed. A German-born musician turned amateur astronomer named William Herschel, scanning the sky one clear night from his own back garden in England using a telescope he had built with his own hands, spotted a faint, slow-moving point of light that at first he took for a comet. Further observation showed something stranger. It moved too slowly and too steadily for a comet, and when its orbit was finally worked out, it turned out to be an entirely new planet, the first ever discovered in recorded history rather than simply known since antiquity. Herschel wanted to name it after his patron, King George III of England, and for a brief while European almanacs politely humored him, but the name that eventually stuck, chosen by others, was Uranus. Word of the discovery crossed the continent by letter within weeks, astonishing an astronomical community that had assumed the roster of planets had been fixed and complete for as long as anyone had studied the sky. When astronomers checked Uranus's measured distance against that old, half-doubted pattern of numbers, it matched almost perfectly. Overnight, a parlor trick became a genuine prediction that had just been proven correct, and suddenly, serious people who had shrugged off the arithmetic for a generation were eager to take the whole idea seriously. And that same pattern of numbers contained one uncomfortable, glaring gap between the orbits of Mars and Jupiter, precisely where the sequence insisted a planet ought to be sitting. There was nothing. No fifth world had ever been found there, in a stretch of sky that astronomers had been studying for as long as anyone had been pointing a telescope upward at all. If the sequence had genuinely predicted Uranus before anyone found it, then simple logic said a planet was still waiting to be discovered in that empty gap, hiding somewhere in plain sight, patiently waiting for the right person to look in the right direction on the right night. By the final years of the 1700s, This had stopped being idle curiosity among a handful of stargazers and had become an organized, continent-spanning project. Franz Xaver von Zach, the Hungarian-born astronomer who eventually pulled the search together, had spent years running an observatory for the Duke of Saxe-Gotha and had grown convinced, well before anyone else, that the missing planet was a solvable problem rather than a permanent mystery, provided enough careful eyes were watching the right patches of sky on the right nights. In the year 1800, he invited 24 observers scattered across Europe, from Germany and Hungary to England and beyond, to divide the predicted planet's expected path across the sky into a series of sections, each roughly 15 degrees wide, with each astronomer assigned one slice of stars to guard, night after night, for anything that moved against the fixed and unmoving background behind it. Among themselves, they adopted a half-joking, half-serious nickname that has outlived nearly everything else about their search: the Celestial Police. Letters describing each man's assigned patch of sky and reminders to report anything unusual at once traveled slowly between cities by post, so that an observation made on a Tuesday night in one country might not reach a colleague in another for the better part of a month, and an entire search could rise and fall on which post rider happened to be riding fastest that week. Heinrich Olbers, already well known and well regarded for his comet work, was one of the 24 astronomers personally invited to join them, each one assigned his own quiet stretch of stars to watch over. The actual work of guarding a slice of sky was tedious in a way that no adventure story would ever bother depicting. It meant sitting outdoors or at an open window through the coldest hours of the night, comparing a hand-drawn star chart against the real sky star by star, checking whether any single point of light had wandered even slightly out of place since the last clear night, sometimes weeks earlier. Clouds could erase an entire season's progress. A single missed comparison could let a genuine discovery slip past unnoticed for years. It was not glamorous work, and it rewarded exactly one kind of person: someone patient enough to keep doing it, night after night, long after the novelty had worn off. He never got the chance to make the first arrest. On the very first night of the new century, the 1st of January, 1801, an astronomer named Giuseppe Piazzi was quietly going about the unglamorous business of updating a star catalogue when he noticed something that did not belong. Piazzi was an Italian priest as well as an astronomer, a professor of mathematics who had gone on to direct the observatory at Palermo and cataloguing the fixed positions of stars, one patient measurement at a time, was exactly the kind of careful, unglamorous labor his position called for. He was not even a member of the organized search. That particular night, he was simply doing his job, checking a small patch of sky against existing star charts, when he noticed a faint point of light sitting where his chart said nothing should be, a point of light that had shifted position ever so slightly from where it had appeared the night before. Piazzi was a cautious man by temperament, and his first assumption was the least dramatic one available, that he had simply stumbled across a comet, a genuinely common event that rarely changed anyone's career or reputation. He tracked the object patiently for several weeks, carefully logging its position on every clear night, until illness slowed him down and the object itself began drifting toward the glare of the sun. As it slipped out of view behind that glare, it took with it any easy way of confirming exactly where it would reappear once the night sky went dark again months later. For a stretch of time that must have felt considerably longer than it actually was, it seemed entirely possible that the discovery of a lifetime had simply been misplaced, swallowed by sunlight, gone before anyone else even had the chance to confirm it was real. Piazzi wrote cautiously to colleagues across Europe describing what he had seen, careful even in his own letters not to overclaim. And for months afterward, astronomers in observatories from Berlin to Paris debated what, exactly, had briefly appeared over Palermo and then vanished again, and whether it would ever be seen a second time. Word of a possible new planet, sighted and then lost again, spread through Europe's small astronomical community the way the best gossip always does, slowly and then all at once, and it did not take long for reactions to split. Some colleagues were cautiously thrilled, eager to believe the missing world had finally been glimpsed, even if only for a few weeks. Others, more skeptical by nature, suspected an error, a smudge on a lens, a star simply misidentified by a tired observer working too late into the night. Piazzi's careful, methodical reputation worked in his favor here. He was not a man given to exaggeration, and colleagues who might have doubted a bolder claim from someone else were inclined to take his cautious account seriously. Still, caution alone could not put the object back in the sky. Something else would have to do that. It was recovered not by a sharper telescope, but by mathematics. A young German mathematician, only 24 years old, named Carl Friedrich Gauss, heard of Piazzi's predicament and treated it as a personal challenge worth solving. Even at that age, Gauss was already gaining a quiet reputation among mathematicians as someone who solved problems other people had simply given up on. And Piazzi's lost object was exactly the sort of impossible-sounding puzzle he seemed to enjoy most. The trouble was a simple one to state, and a brutal one to actually work out. A handful of observations covering only a short arc of sky is, mathematically speaking, nowhere near enough information to describe a full, closed loop around the sun with any confidence. And every astronomer who had tried to project Piazzi's scattered points forward into a usable prediction had come up with a different, unreliable answer. Working from nothing more than that same brief handful of recorded positions, Gauss developed an entirely new method for calculating a complete orbit from limited and scattered data, a piece of mathematics so far ahead of anything available at the time that versions of it are still taught to students today. Where other astronomers had produced a range of vague guesses, Gauss produced a single, confident position telling the astronomical community, in effect, to look there and nowhere else. On the last night of 1801, both Franz Xaver von Zach and Heinrich Olbers separately pointed their telescopes toward that calculated spot, and the faint point of light was waiting for them exactly where Gauss's arithmetic said it would be, closing out the first year of the century with the very discovery it had opened. Piazzi's discovery was given a name, Ceres, after the old Roman goddess of the harvest, and for a short while it genuinely seemed that the missing planet had finally been run to ground. Its position matched the old numerical pattern closely enough that the celestial police and much of the wider astronomical world along with them were more than ready to close the case for good. Early almanacs listed it plainly as a planet, the fifth from the Sun, taking its place beside Mercury, Venus, Earth, and Mars without qualification. A fifth planet, small and faint but exactly where the mathematics had insisted it must be, had apparently been sitting there all along, patiently waiting to be noticed by whoever happened to be updating the right star catalogue on the right night. That particular confidence lasted about 15 months. Olbers had been one of the astronomers who helped confirm Ceres using Gauss's calculations, and once it was safely back in view, he kept his own telescope trained on that same patch of sky, curious to study this new addition to the solar system further, and, quietly, hoping to be useful again if anything else turned up nearby. On the night of the 28th of March, 1802, something did. He found a second faint, slowly moving object, sitting in almost the same neighborhood of orbits as Ceres, in a stretch of sky that, by every expectation of the previous year, should have contained exactly one planet and nothing else. He named it Pallas, after the goddess of wisdom, and reported the discovery to his colleagues with the same careful precision he brought to everything else. But underneath that careful precision, something had clearly unsettled him. A single planet had been expected in this gap between Mars and Jupiter. Now, without warning, there appeared to be two, and neither one looked quite the way a planet was supposed to look through a telescope in the first place. That last detail mattered more than it might seem. When William Herschel had found Uranus 2 decades earlier, it had shown a small, steady disk of light, under magnification, a tiny round shield rather than a pinpoint, the way any true planet is supposed to look once a telescope is turned up strong enough. Ceres and Pallas showed no such disk at all, no matter how much magnification astronomers tried against them. They looked, through even the finest instruments of the day, exactly like distant stars, sharp, dimensionless points of light, indistinguishable from the fixed background around them except for the slow, patient drift that gave them away night after night. Herschel himself, studying the reports from his own English garden, proposed a new word for this strange in-between category of object, one that looked star-like rather than planet-like, even though it plainly moved and orbited like one, and the term he coined, asteroid, meaning roughly star-shaped, has stuck to this category of object ever since. A small piece of linguistic evidence that astronomers of the time already sensed they were looking at something that did not fit comfortably into either of their two existing boxes. To anyone watching through a telescope on a clear night in Bremen or Palermo or anywhere else in Europe, these new discoveries offered no dramatic image at all, no visible surface, no hint of shape or texture, nothing but a single steady point of light, indistinguishable from any of the thousands of true stars surrounding it, patiently waiting to be caught in the act of drifting. Once their sizes could be reasonably estimated from how much light they reflected, both objects turned out to be startlingly, almost embarrassingly small, to match that missing planet role. Ceres measured only a few 100 miles across, something like a quarter the width of our own moon, and Pallas was smaller still. Neither one came anywhere close to the scale of a genuine planet, and yet here they both were, occupying almost exactly the stretch of orbit where a full world was supposed to exist, and, more strangely still, tracing orbital paths, tilted and stretched in ways that no two members of one tidy, planetary family ought to share by simple coincidence. Olbers turned the puzzle over in his mind for some time and arrived at an explanation that must have felt, given everything in front of him, like the only sensible one left standing. If a complete planet had once occupied this part of the solar system, and what remained now was two small, oddly matched fragments traveling suspiciously related paths around the sun, paths that looked as though they might once have crossed at a single shared point long ago, then perhaps the planet had not simply failed to form in the first place. Perhaps it had formed, existed for some unknown stretch of time, and then been violently destroyed, torn apart by some catastrophic event, possibly a collision with a passing comet, leaving Ceres and Pallas behind as its scattered wreckage, still drifting slowly, apart from whatever point in space the shattering had first begun. It is worth pausing on just how sensible that idea genuinely was, given everything Olbers had in front of him at the time. He was not being careless, and he was not reaching for drama for its own sake. Two small, star-like bodies, sharing a neighborhood where exactly one planet had been confidently predicted, tracing paths that hinted at a common origin, is a genuinely strange result, and a shattered world was, in the year 1802, a tidy and reasonable explanation for a strange result. Nothing in the physics available to Olbers at the time ruled the idea out. There was no understood mechanism in that era by which a planet could simply fail to assemble itself out of raw material in the first place. No accepted reason why a region of space should stay permanently, deliberately unfinished. Worlds either existed or they had once existed and been destroyed. Those were the only two categories anyone had reason to imagine, and between the two, Olbers had chosen the one the evidence in front of him actually seemed to support. If anything, every new measurement he was able to make over the following years seemed to lend the destruction theory further weight rather than weaken it. Not every astronomer accepted the idea immediately or without question. A hypothesis this dramatic, coming from a physician better known for his comet calculations than for grand theorizing, invited its share of polite doubt in the letters that circulated among the celestial police in the months that followed. Some wondered whether two objects were simply too small a sample to justify talk of an entire vanished world. Others found the destruction theory the only thing that made any sense of the tangled, overlapping orbits, Ceres and Pallas, traced around the Sun, and said so plainly in their own replies. Von Zach himself, who had organized the whole search in the first place, corresponded with Olbers about the idea at length, turning it over from several angles before largely coming around to it. It was, in other words, debated the way any serious new idea in a small, close-knit scientific community tends to be debated carefully and at length, long before it hardened into the confident textbook fact it would later become. And then, rather than fading away, the fragments kept turning up. In 1804, a German astronomer and fellow member of the search, named Carl Harding, working at a private observatory near Bremen, not so very far from Olbers's own rooftop, and continuing the same patient survey work that had already turned up two objects in this crowded neighborhood, discovered a third, Juno. It was smaller again than either Ceres or Pallas, but it occupied yet another orbit in that same narrow stretch of sky, and to observers already convinced that a planet had been destroyed there, it looked for all the world like one more scattered piece of the same broken body, further confirmation arriving right on schedule. Olbers, now genuinely certain that additional fragments were waiting to be found by anyone patient enough to look, kept searching that same region himself, refining his methods, and returning to the identical patch of sky, night after night, month after month, in the same upstairs room where he had once nursed a comet's path into mathematical order and would soon do the same for a shattered planet. There is something worth sitting with in that image. A doctor, finished with his last patient of the day, climbing a narrow staircase alone, lighting a single lamp, and settling in for hours of patient, quiet watching, waiting for a change so small that most people would never notice it at all. On the 29th of March, 1807, almost exactly 5 years to the day after he had first found Pallas, his patience was rewarded once more. He discovered a fourth object, larger and considerably brighter than the previous three, and he allowed the same young Gauss, whose orbital mathematics had recovered Ceres 6 years earlier, to choose its name. Gauss called it Vesta, after the Roman goddess of the hearth and home, a fittingly domestic name for an object found by a physician who did his most important work without ever once leaving his own house. Vesta turned out to be different from its three predecessors in one notable way. It was bright enough, on a clear night, to be seen with the naked eye alone, without any telescope at all, the only member of this new and puzzling family that could make that claim. For a public that had never once glimpsed Ceres or Pallas or Juno directly and had only ever read about them in letters and journals, Vesta offered something closer to proof they could witness for themselves: a faint star hanging in a familiar patch of night sky that had not been there at all a few years earlier, and now quietly was. 4 separate objects now, all sharing that one crowded gap between Mars and Jupiter, all far too small individually to be the missing world the old numerical pattern had promised, and all of it, in the thinking of the day, treated as further proof that something had gone catastrophically wrong in this part of the solar system, rather than proof that nothing had ever been meant to form there in the first place. For the astronomers of the early 1800s, and for the many generations of writers, illustrators, and eventually filmmakers who would go on to inherit their conclusions without necessarily inheriting their caution, this had long since stopped being one careful physician's tentative hypothesis and had simply become how the region was understood. A world had lived here once. The story went. Something had ended it violently. What remained afterward was wreckage, scattered across a great, ruined orbit, drifting slowly apart at speeds no one yet had the means to properly measure. And wreckage, by its very nature, is the sort of thing you have to be careful crossing. The old arithmetic that had started the whole search, meanwhile, quietly faded from the story it had helped set in motion. When Neptune was finally discovered decades later, its actual distance from the Sun refused to match what the Titius-Bode pattern predicted, and the elegant numerical sequence that had once seemed to reveal a genuine law of nature was gradually reclassified as a curious coincidence after all, useful for pointing early astronomers toward a real question, but never actually explaining anything on its own. The search it had inspired, though, and the conclusion that search arrived at, proved to have a far longer life than the arithmetic that started it. For nearly a century afterward, that conclusion held its ground almost entirely unchallenged, settling comfortably into astronomy textbooks and popular accounts alike, quietly waiting to be passed along to whichever new medium eventually took over the job of picturing the solar system for ordinary people. Later discoveries only seemed to deepen it rather than complicate it. Astronomers kept finding more of these small, star-like bodies scattered through the same general neighborhood, dozens of them within a few decades, then hundreds within a century, and each new one was folded easily into the same tidy story of a single ancient catastrophe, one more piece of debris from the same long-ago wreck. Popular lecturers and early science writers, eager for a story with real drama in it, passed the destroyed planet idea along to audiences who had never looked through a telescope in their lives, retelling it at public lectures and in the pages of illustrated magazines meant for parlors rather than observatories. Each retelling simplified the story a little further, trimming away Olbers's careful hedging and his colleagues' early debates, until what remained was simply the dramatic core: a planet, a catastrophe, a field of wreckage. By the time illustrated encyclopedias, and eventually motion pictures, needed a way to picture that stretch of space, the wrecked planet was the only version of the story most of them had ever inherited, passed down so many times over so many decades that its origin, as one careful physician's best guess, made in good faith with the evidence available to him, had been almost entirely forgotten along the way. It was, in its way, a satisfying explanation precisely because it asked nothing further of anyone. The planet had existed. The planet had died. What remained was simply what remained, and there was nothing more to explain. It would take a very different kind of evidence, gathered by a very different kind of astronomer, asking a question that nobody in Olbers's own generation had seriously thought to raise, before anyone began to wonder whether a planet had ever actually existed in that gap to be destroyed in the first place. That question, once someone finally asked it, would turn out to be far stranger and far more interesting than the shattered world Olbers had proposed. Set the wrecked planet aside for a moment, the way astronomers eventually had to, and look instead at what a telescope, and eventually a spacecraft, can actually measure out there, patiently, one careful observation at a time. Once you stop imagining and start counting, the numbers tell a very different story than the one that held for a century, and they tell it with very little room left for argument. Start with distance, since distance is the simplest thing to measure and the hardest thing to actually picture. Astronomers now estimate that the average gap between one asteroid and its nearest neighbor in the main belt runs somewhere between 600,000 and 730,000 miles. To put that in terms that means something on a human scale, imagine driving from one coast of the United States to the other, roughly 3,000 miles of highway, windshield to windshield, and then making that same cross-country trip again and again, more than 200 times over, before you finally reached the next rock. Or picture it a different way. The distance between the Earth and its own moon, a gap that already looks enormous from a back porch on a clear night, is only about 240,000 miles. The typical stretch of nothing between two neighboring asteroids is roughly 3 times that distance, an emptiness so much larger than the emptiness already separating us from our own nearest neighbor in space that the comparison barely helps at all. Stand on the surface of one asteroid, and in almost every direction there would be nothing to see but stars. Not a looming shape in the middle distance, not a shadow crossing the sky, nothing. The neighbor you are supposedly crowded against would very likely be invisible to your own eyes, lost somewhere in that same ordinary field of stars that fills the rest of the sky, indistinguishable from any other faint point of light, unless you already knew precisely where to look. That spacing is an average, which means the true picture is even stranger than a single number suggests. In places, 2 asteroids might drift somewhat closer together than that. In others, the gap stretches even wider, a stray boulder or 2 tumbling alone through a stretch of darkness so vast it would take a beam of light itself the better part of an hour to cross. There is no wall of rock anywhere in the belt. There is no wall of anything. There is simply an enormous ring of largely empty space, patrolled by a scattered population of solid bodies too far apart to ever meaningfully crowd one another, held loosely together only by the same gravity that keeps every other object in the solar system in its lane, each one indifferent to the others, each one following its own slow, private orbit around the sun for millions of years at a stretch, without ever coming remotely close to another. The total amount of material scattered across that vast space is smaller still than the distances alone suggest. Add up every asteroid ever catalogued in the main belt, from the largest down to the smallest fleck of gravel too small to ever be individually tracked, and the entire collection comes to somewhere between 3 and 4% of the mass of our own moon. Not the mass of a planet, not even a meaningful fraction of one. A few percent of a single moon, spread across a donut-shaped region of space, wide enough to swallow the Earth's orbit around the Sun several times over. And that modest total is not spread evenly. More than half of it belongs to just 4 objects: Ceres, Vesta, Pallas, and a 4th, somewhat less famous body named Hygiea. Ceres alone, the very first object Piazzi ever found, accounts for something close to 1/3 of the entire belt's mass, all by itself. A single, small world, carrying more material than every other asteroid in the belt combined. Vesta, the brightest of the group and the only one ever visible to the naked eye, holds a large share of what remains, its bright, battered surface reflecting enough sunlight to be picked out from Earth by a patient observer who knows exactly where and when to look. Pallas, Olbers's own discovery, follows its own steeply tilted orbit, carrying it well above and below the flat plane where most of the rest of the belt travels. A small reminder of just how little order Olbers's shattered planet story actually managed to explain even at the time. And quiet, rarely mentioned Hygeia, discovered decades after the others and named for the Greek goddess of health, divides up most of what is left with Pallas between them. Everything else, every other asteroid ever catalogued, every single one of the hundreds of thousands of smaller bodies scattered across that enormous ring, shares whatever little is left over once those four have taken their portion. And there are a great many other asteroids to share what little remains. Modern sky surveys, sweeping the same stretch of space that Olbers and Harding once searched one careful comparison at a time, working alone with a hand-drawn chart and a cold telescope, have now catalogued more than 1,300,000 individual objects in the main belt, each one with a confirmed, tracked orbit, where a 19th century astronomer might spend an entire clear night comparing a single small patch of sky against a paper chart, hoping to notice one faint point of light out of thousands that had quietly shifted position. Modern observatories now sweep that same amount of sky in a matter of minutes, photographing it again and again over the course of a night and letting a computer do the tedious work of comparing one image against the last, flagging anything that has moved even the smallest amount for a human researcher to review the next morning. A new generation of wide-field telescopes, built specifically to photograph enormous swaths of sky repeatedly over the course of years, is only just beginning full operations, and early results suggest the total catalogue of known asteroids could grow by a very large margin within just the first few years of steady observation. That number climbs every week as a result, far faster than any single observer working alone could ever manage. 1,300,000 confirmed object sounds, at first hearing like exactly the kind of crowded, hazardous field the old story promised. It is only once you remember how much open space those objects are spread across that the picture flips entirely. 1 million objects, each one a genuine solid body with its own name or number and its own carefully tracked orbit, and still, on average, hundreds of thousands of miles of nothing between any two of them. Both things are true at once, and neither one cancels the other out. The belt genuinely does contain more than 1 million individual, catalogued worlds, more than any single region outside it in the entire solar system. And the belt is also, by any honest measure of density, one of the emptiest volumes of space that still happens to contain something solid at all. Popular imagination has always struggled to hold both of those facts in mind simultaneously, reaching instead for the simpler, more dramatic version, the one where 1 million objects automatically means a crowded, dangerous field, rather than 1 million lonely points of light scattered almost unimaginably far apart from one another. Picture the shape of the region itself for a moment, not just the gaps between individual rocks within it. The main belt is not a flat ring but a thick donut of space, stretching from roughly 2 2/10 to 3 2/10 times the distance between the Earth and the Sun, and standing nearly as tall, top to bottom, as that same Earth-to-Sun distance all on its own. It is a genuinely three-dimensional volume, not a narrow lane, and the handful of percent of a moon's worth of material sitting inside it is spread through every part of that volume, above and below the flat plane, where the planets orbit as much as around it. Most asteroids do drift close to that flat plane, the same broad, invisible sheet the planets themselves roughly share. But plenty wander well above and below it too, tracing tilted, looping paths that carry them out of that plane and back again over the course of years, adding an entire extra dimension of separation on top of the enormous distances already spread across the flat map. Most illustrations show a few percent of a single moon distributed through a region that size does not make for a crowded neighborhood under any honest reading of the numbers. It makes for one of the emptiest volumes of real estate in the entire solar system that still happens to contain anything solid at all. Numbers on a page are one kind of evidence. A machine built by human hands sent out to actually make the crossing and report back honestly on what it found is another kind entirely, and it is a kind that nobody could argue with once it existed. That machine was called Pioneer 10, and in the summer of 1972, it became the first spacecraft in history to attempt what Olbers and his contemporaries would have considered close to a death sentence. Flying directly through the region their own science had assured them was littered with the wreckage of a destroyed world. No one had ever tried before, in the literal sense that mattered most. Every earlier human journey, whether by ship, by aircraft, or by earlier spacecraft bound for the moon, had stayed within the well-mapped, well-understood inner solar system. Pioneer 10 was aiming for territory no one had any direct experience with at all. Pioneer 10's ultimate destination was Jupiter itself, the first close encounter any spacecraft would ever have with the giant planet. But before it could reach Jupiter, it first had to answer a much older and, in its own way, more fundamental question. Engineers had equipped the spacecraft with instruments specifically designed to count the impacts of tiny dust particles along the way, small pressurized panels built to register the faintest puncture, a kind of early warning system that would, at the very least, tell mission control exactly how much material the spacecraft was passing through, even if nothing larger ever appeared, turning what could have been a total unknown into something at least partially measurable in real time. Nobody involved in the mission treated the crossing lightly. This was not a stunt, and it was not theater staged for the sake of drama. Engineers at NASA genuinely did not know, in any precise or confident way, how many hazardous fragments were actually out there or how likely the spacecraft was to strike one. The belt had never been tested. No probe, no satellite, nothing built by human hands had ever attempted to cross it before, and the honest answer to how dangerous it might be was that nobody could say for certain. Working from the best estimates available at the time, drawn from telescope surveys that could only detect the largest objects and had to guess at everything smaller, mission scientists calculated something close to a 9 in 10 chance that Pioneer 10 would make it through completely unscathed, which meant they were also quietly accepting something close to a 1 in 10 chance that it would not. That is not the language of people confident there was nothing to worry about. That is the language of people taking a real, calculated risk, deliberately, with their eyes open, because there was no other way to find out the truth than to actually go and look. No amount of careful mathematics, on paper, no matter how rigorous, could substitute for a single spacecraft actually making the journey and reporting back what it found. They took every precaution available to them. Pioneer 10's trajectory was planned with extraordinary care, threading a path that kept the spacecraft more than 5 million miles from the nearest asteroid, whose orbit was precisely known at the time planning began, a margin chosen specifically to avoid the one hazard mission planners could actually see coming, even as they braced for the countless smaller hazards they could not. Every known object with a reliably charted orbit was checked and rechecked against the planned flight path in the months before launch, a painstaking exercise in subtraction, ruling out one danger at a time from a list that could never be made entirely complete. Since the smallest and most numerous objects in the belt remained, and still largely remain, far too faint for any telescope of that era to have ever catalogued individually. On the 15th of July, 1972, having already raced past the orbit of Mars faster than any object built by human hands had ever traveled before it, Pioneer 10 crossed into the belt itself and began a passage that would take the better part of a year, roughly the length of a full school year, stretched from the first cool days of autumn through the following spring, 7 long months during which the spacecraft's radio signal, faint and steady, remained the only proof to anyone on Earth that it was still out there, still intact, still traveling. For 7 months, the spacecraft traveled through the very stretch of space that popular imagination had spent more than a century picturing as an obstacle course, sending back a steady stream of instrument readings the entire way, readings that engineers on the ground studied closely for any sign of trouble, any spike in the meteoroid detectors that might suggest the density of debris was greater than anyone had planned for. On the 2nd of December that same year, it made its closest approach to any individually tracked asteroid, an object named Nike, passing within several million miles of it, closer than it would come to any other identified body during the entire crossing, and even that counted as a wide, comfortable berth by any ordinary measure of distance, farther than most people will ever travel from home in an entire lifetime, and farther still than the distance separating most of the belt's other inhabitants from one another on an ordinary night. In February of 1973, Pioneer 10 emerged on the far side of the belt, safely and without drama, on course for its rendezvous with Jupiter, having completed the crossing without a single meaningful incident. If you could have ridden along inside that spacecraft for those 7 months, there would have been remarkably little to report. No tumbling boulders rushing past a window, no sudden flashes of impact, no shuddering course corrections. Only the slow, patient hum of instruments recording a whole lot of nothing, hour after hour, day after day, broken occasionally by a faint, harmless tick as a grain of dust, no larger than a speck of flour, brushed against the hull and moved on. Newspapers covering the story at the time noted, almost as an afterthought, that the only material the spacecraft had actually picked up along the way was that same kind of fine, ordinary dust that drifts through every corner of the solar system, the sort of thing that settles gently onto any spacecraft over a long enough journey and means nothing at all. There had been no debris field to dodge. There had been no near misses, no damaged instruments, no drama of any kind. There had simply been 7 months of quiet, uneventful travel through open space, followed by confirmation that the crossing everyone had worried about was, in fact, entirely survivable, and had perhaps never been quite as dangerous as the era's imagination had assumed. That first crossing settled a question nobody had ever been able to answer with certainty before. Every crossing since has only reinforced the answer, and the emotional distance between that first anxious 9 in 10 calculation and the way engineers plan a belt crossing today is its own kind of evidence. Modern mission planners barely give the asteroid belt a second thought when charting a course toward the outer solar system. It has become, in the space of only a few decades, one of the least worrisome legs of an interplanetary journey, a stretch of paperwork and routine trajectory planning rather than a genuine hazard to be nervously calculated around. The fear that shaped 1972 has simply evaporated, replaced by a confidence built on nothing more mysterious than repeated, uneventful experience. Pioneer 10's sister craft, Pioneer 11, followed the same general path a year later, on its own way to Jupiter and eventually Saturn, and made the crossing just as safely, using the confidence gained from its predecessor's success to plan an even more ambitious route. Both Voyager spacecraft passed through on their way to the outer planets in the final years of that same decade, carrying with them the famous golden records meant to represent humanity to any distant listener who might one day find them. Sailing through the supposedly hazardous belt without so much as a scratch on either record's polished surface, and sending back their own uneventful reports. The Galileo spacecraft crossed the belt twice during its own long journey toward Jupiter in the 1990s, pausing along the way to photograph two individual asteroids up close for the first time in history, close enough to see their battered, cratered surfaces in real detail rather than as mere points of light. The first, a small, irregular body named Gaspra, appeared in 1991 as a lumpy, cratered potato tumbling silently through the dark, the first genuine close-up portrait of an asteroid ever taken by human instruments. 2 years later, Galileo photographed a second asteroid, named Ida, and buried in those images was a discovery nobody on the mission team had expected: a tiny companion, barely a mile across, quietly orbiting Ida of its own accord. Astronomers named it Dactyl, and it became the first confirmed proof that even these small, scattered fragments could have moons of their own, tiny worlds, orbiting slightly larger worlds, all of it tumbling peacefully through supposedly hazardous space without incident. The Cassini spacecraft crossed on its way to Saturn, gathering data the entire way before beginning what would become a 13-year study of that ringed planet and its many moons. A mission called Stardust threaded through the belt more than once, while chasing down a comet, eventually flying through the comet's surrounding cloud of dust, collecting a sample and returning it safely to Earth, a round trip that carried it back and forth across the very region Olbers had once judged too dangerous to approach. The European Rosetta spacecraft crossed twice, visiting 2 more asteroids along its own long road toward a comet of its own, close enough on each pass to add 2 more detailed portraits to the growing gallery of small worlds, photographed up close rather than merely inferred from a distant point of light. Japan's Hayabusa missions crossed the belt entirely, out and back, to visit and return samples from 2 separate small asteroids, journeys that would have been unthinkable if the old story about a destroyed world had ever been true. Each spacecraft threading its way to a specific target and home again across the same stretch of space Olbers had once judged too hazardous to approach even in passing. New Horizons crossed on its way toward Pluto in 2006. Juno crossed on its way toward Jupiter, arriving safely years later to begin its own long study of that giant planet's interior and its swirling violent storms. In the 2020s, a spacecraft named Lucy became the latest to make the passage, launched on a 12-year journey toward a swarm of asteroids that share Jupiter's own orbit, pausing along the way to photograph 2 small main belt asteroids up close as practice runs for the more distant targets still ahead of it. A mission named Psyche is currently making the same crossing right now, on its way to study a strange, metal-rich asteroid of its own, one that scientists suspect may be the exposed core of a much larger world that lost its outer layers billions of years ago, stripped away by collisions rather than by any single catastrophic event. None of these missions needed to dodge anything. None of them required so much as a single unplanned course correction to avoid a collision. They simply pointed themselves in the right direction and flew, the way a ship crosses open ocean rather than picking its way through a harbor choked with wreckage. One mission did more than simply pass through. It stayed. A spacecraft named Dawn spent years living inside the very region Olbers had once described as a graveyard, rather than merely crossing it. Dawn settled into orbit around Vesta in the summer of 2011, spending more than a year circling that single asteroid and mapping its surface in extraordinary detail, revealing towering cliffs and an enormous impact basin near its southern pole, nearly as wide as the asteroid itself, evidence of an ancient collision violent enough to have very nearly shattered Vesta on its own. And yet Vesta had endured, whole and intact, orbiting peacefully ever since. Dawn then fired its unusual ion engine, a propulsion system that pushes a spacecraft forward, not with a single dramatic burn, but with a continuous, gentle thrust, sustained for months at a time, and set off for a second destination entirely, something no earlier spacecraft had ever attempted after already settling into orbit around one body. It arrived at Ceres in the spring of 2015 and remained there for years afterward, orbiting patiently, close enough to photograph individual craters and strange, bright surface deposits that would later turn out to be salt left behind by ancient briny water, until its fuel finally ran out in the autumn of 2018, and its instruments fell silent for good, leaving it to drift in a stable, harmless orbit around Ceres indefinitely. For the better part of a decade, a piece of human machinery lived, quite literally, inside the supposed wreckage field, orbiting peacefully within it the entire time, circling two of the very objects Olbers had once described as pieces of a shattered planet, never once threatened by the crowded, dangerous environment the popular imagination had insisted must surround it. Perhaps no one has said it more plainly than the scientist who led the New Horizons mission during its own crossing on the way to Pluto in 2006, a mission that would go on to give humanity its first close look at that distant, icy world nearly a decade later. Asked about the odds of the spacecraft actually striking something during its passage through the belt, the mission's principal investigator explained, in terms any listener could understand without a background in astronomy, that the true danger was closer to 1 chance in a billion than any number worth losing sleep over, so small that the far bigger challenge for scientists hoping to study an asteroid up close was actually aiming for one on purpose, since simply passing through guaranteed nothing but empty space in every direction. It is a small, almost funny irony worth sitting with. The very same emptiness that once convinced Olbers a planet must have been destroyed here is the exact quality that now makes deliberately visiting one of these objects, rather than merely passing near it by accident, the genuinely difficult part of the job. That is not the assessment of someone downplaying a real danger for the sake of good publicity. It is the plain, considered judgment of a scientist who had actually sent a spacecraft through the region and watched the data come back, mission after mission, with the same quiet result every time. That total, staggering as it already sounds, still represents only the objects large enough and reflective enough for a telescope to have caught and confirmed. Countless smaller fragments, boulders and pebbles, too faint to register individually against the darkness, almost certainly outnumber the catalogue million by a wide margin, tumbling silently through the same enormous volume, unnamed and untracked, contributing their own small, forgettable share to that same 3 or 4% of a moon's worth of material. Even accounting for every last one of them, actually finding them out there, adrift in a region this large, remains far closer to searching for a specific grain of sand somewhere across an entire ocean than to picking a path through a crowded room. A difference in scale that no single number on a page can quite capture, no matter how carefully it is chosen. Every single piece of this evidence points in the same direction, and it is worth sitting with just how thoroughly it contradicts everything Olbers and his contemporaries believed. 100 years of astronomers, working from a scattering of small, oddly matched objects and a plausible-sounding story about a shattered world, had pictured this region as dense, dangerous, and violent, a place a traveler would need real luck to cross safely. The actual measurements gathered patiently over more than half a century of spaceflight say the opposite. Wide open, overwhelmingly empty. Safe enough that a single spacecraft could park itself there for the better part of a decade without incident. Safe enough that more than a dozen separate missions have threaded through it without so much as a scare. Safe enough that engineers now plan these crossings as a routine, almost forgettable leg of a much longer journey rather than the central hazard of the mission. None of this required a single new law of physics to establish. It only required someone, eventually, to actually go and look patiently, mission after mission, rather than simply trusting the most dramatic story available. Which raises a question the old story never had to answer, because the old story never needed to. If Ceres and Pallas and every other object out there really were the shattered remains of a single destroyed world, then where, exactly, did the rest of that world go? A full-size planet does not simply vanish down to 3 or 4% of a moon's worth of debris and leave nothing else behind. Something would have had to carry the missing mass away, scatter it, disperse it far beyond anything a telescope on Earth or a spacecraft passing through could ever hope to recover. That missing mass is not a small accounting error to wave away. If the old, comfortable story were true, entire planets' worth of rock and metal would need to have been flung somewhere else in the solar system, or out of it entirely, by a single act of destruction dramatic enough to account for all of it at once, and yet leave behind no other trace of that destruction anywhere astronomers have ever thought to look. Olbers never had an answer to that question, because in his era, nobody had yet worked out the mechanism that could actually do it, or even imagined that such a mechanism might exist at all. He had two small, star-like objects in front of him, an old prediction that insisted a planet belonged in this exact patch of sky, and no understood way for a region of space to simply decline to build one. Given those choices, destruction was the only door left open to walk through. It would take another astronomer entirely, working nearly a century later, approaching the problem from a direction nobody in the Celestial Police had ever thought to consider, before that door finally closed and a different, far stranger one opened in its place, one that had nothing to do with a comet or a collision or any single dramatic moment of violence at all. The true answer had been sitting in plain sight the entire time, written quietly into the orbits of the asteroids themselves, waiting patiently for someone with enough patience and enough curiosity to actually sit down and do the arithmetic properly. The man who finally sat down and did that arithmetic was not looking for a missing planet at all, and he was not hunting for fame or a dramatic new discovery the way so many of the Celestial Police's original members had been. He was simply trying to make sense of a pile of numbers that, on the surface, should never have meant anything at all, working through them the patient, unglamorous way, one column at a time, on an ordinary desk far from any observatory dome. His name was Daniel Kirkwood, an American mathematician and astronomer working at a small college in Indiana, about as far from the observatories of Bremen and Palermo as it was possible to be, and still be doing the same kind of careful, patient work. Kirkwood had spent years teaching mathematics to college students long before he ever turned his full attention to the asteroid belt, and that background shows in how he eventually solved the puzzle, favoring quiet arithmetic over the nightly vigil at an eyepiece that had defined Olbers's own approach 2 generations earlier. He was not primarily an observer, chasing new discoveries the way Olbers once had, hunting the sky night after night for some faint point of light nobody had noticed before. His talent was different, and in its own quiet way just as rare. He was a careful reader of tables, the sort of scholar who could stare at a long column of orbital measurements longer than almost anyone else and notice the one detail that did not belong, patiently working through arithmetic that other astronomers, more interested in the thrill of a new discovery, had simply never bothered to perform. What he noticed, once he laid out the known asteroids by how far each one orbited from the Sun, arranging them in a single long table with distance in one column and the count of known objects in the next, was a pattern that had nothing to do with fragments or explosions at all. It was the kind of pattern that only reveals itself to someone willing to do the tedious, unglamorous work of actually building the table in the first place, rather than simply admiring the individual discoveries one at a time, the way most of Kirkwood's contemporaries preferred to. By the 1860s, decades after Olbers had proposed his shattered world, and decades after Harding and Olbers himself had added Juno and Vesta to the growing list of fragments, astronomers had catalogued far more of these small bodies than anyone in the Celestial Police could ever have imagined finding, giving Kirkwood a far richer set of tables to work from than had existed in Olbers's own lifetime. At certain very specific distances, there were almost no asteroids whatsoever, clean, narrow gaps in an otherwise fairly continuous distribution, as if something had reached in and swept those particular lanes empty on purpose. On either side of each gap, asteroids were plentiful, orbiting comfortably at distances just slightly closer to or farther from the Sun. Inside it, next to nothing. This was not the ragged, uneven pattern you would expect from a world torn apart at random by a single ancient collision, the kind of pattern that had satisfied Olbers and his contemporaries for the better part of a century. A genuine explosion scatters its debris more or less indiscriminately, thinning out gradually with distance rather than leaving sharp, surgical gaps at precise, mathematically predictable locations. What Kirkwood was looking at instead had the fingerprints of something deliberate and ongoing, a pattern imposed by a rule rather than an accident, repeating itself with a regularity no single moment of violence could ever produce. He worked out what that rule was, and the answer had almost nothing to do with the asteroids themselves or with anything that had ever happened to them in the past. It had to do with a much larger neighbor sitting nearby, quietly shaping the entire region without ever needing to strike a single one of them directly. It had to do with Jupiter. Every asteroid in the belt orbits the Sun on its own private schedule, some completing a full circuit in a little over 3 years, others taking closer to 6, depending on how far out they sit, each one indifferent to the others, each one following the same basic law of gravity that governs every orbiting body from the smallest pebble to the largest planet. Jupiter, far larger and far more influential than anything else nearby, takes just under 12 years to complete one full orbit of its own, a slow, steady rhythm that every smaller object in the belt feels to some degree. Whether or not that influence ever becomes strong enough to matter, Kirkwood noticed that the empty gaps in his tables lined up precisely with the distances where an asteroid's own orbital period worked out to a simple, clean fraction of Jupiter's, distances where an asteroid might complete exactly 3 orbits for every one of Jupiter's, or 2 orbits for every one, or 5 orbits for every 2, or 7 for every 3. The widest and deepest of these empty lanes sits at roughly 2.5 times the distance between the Earth and the Sun, where 3 asteroid orbits fit precisely into the time Jupiter takes to complete one. A location so thoroughly swept clean that it still marks one of the sharpest, most visible boundaries in the entire belt. Smaller gaps appear further out and further in, at each of the other simple ratios, each one a little narrower and a little less dramatic than the first, but each one following the exact same underlying rule. At every other distance in between, away from these precise resonant points, an asteroid and Jupiter drift in and out of alignment constantly, and the giant planet's gravitational tug lands at a different point in the asteroid's orbit almost every time, nudging it this way and that in ways that mostly cancel out over the long run. But at those special resonant distances, the 2 objects fall into step with each other, meeting at the same point in their respective orbits again and again, orbit after orbit, for as long as the asteroid remains there. Picture a child on a playground swing and the parent standing behind, giving it the occasional push. Push at a random moment in the swing's arc, and mostly you just interrupt its rhythm, the swing barely noticing, the motion changing only a little before settling back into its usual arc, the way most of the belt's asteroids drift along largely undisturbed by Jupiter's distant, ever-shifting pull. But push at exactly the right moment, at the top of the same point in the swing's motion, again and again, and even a gentle hand can send that swing higher and higher with every pass, the small pushes compounding instead of cancelling out, until the child is swinging far higher than any single push could ever explain on its own. Jupiter's gravity behaves the same way toward any asteroid unlucky enough to sit at one of these resonant distances. Instead of a random scatter of small tugs that average out to almost nothing over time, the asteroid receives the same kind of tug at the same point in its orbit, orbit after orbit, and those tugs add together rather than washing out over thousands and then millions of years. That steady, repeated pull stretches the asteroid's orbit further and further out of its original shape, until eventually the asteroid is flung onto a wildly different path entirely, sent crashing into the Sun, ejected from the belt altogether into the emptier reaches of the outer solar system, or hurled onto a path that crosses the orbit of Mars or even Earth, joining the population of near-Earth objects that occasionally streak across our own night sky, their entire journey traceable back to a single moment, however many millions of years earlier, when they first wandered too close to one of these precise, invisible, resonant lanes. Whatever happens to it, one outcome is guaranteed. It does not stay where it started. The lane empties out, and it stays empty because anything that later drifts into that same resonant distance meets exactly the same fate. Some of that displaced material has traveled a genuinely long way from where this story began. A meteorite recovered from a farm field or a desert somewhere on Earth, cut open and studied in a laboratory, quite often turns out to be a fragment that began its existence somewhere in the asteroid belt, only to be nudged into one of Kirkwood's gaps at some point over the last few 100 million years, flung onto a new, unstable orbit, and eventually carried close enough to Earth to fall from the sky as a shooting star, or occasionally as something heavier landing hard enough to leave a crater. The same resonances that Kirkwood identified as empty lanes in a 19th century table of numbers are still actively feeding material toward the inner solar system today, a slow, ongoing supply chain connecting the gaps in the belt directly to the rocks occasionally found lying in a field long after they fell, or, more rarely, streaking bright and briefly visible across a clear night sky before ever reaching the ground at all, a small, fleeting reminder that the process Kirkwood first noticed in a column of numbers has never actually stopped. This single mechanism, repeated at every resonant distance throughout the belt, explained Kirkwood's gaps completely, and it explained something far larger than Kirkwood himself may have initially realized. If Jupiter's gravity is capable of clearing out narrow lanes at these specific resonant distances, sending anything that lingers there onto some other, more dramatic path, then the same gravity is also capable of preventing anything from ever accumulating in those places at all. A planet does not spring into existence all at once. It builds slowly, over millions of years, as smaller bodies collide and stick together, gradually growing from dust to pebbles to boulders to something planet-sized, a process that depends entirely on those smaller building blocks being able to linger near one another long enough for gravity and simple physical contact to do the rest. Everywhere else in the young solar system, that patient process eventually succeeded. Mercury, Venus, Earth, and Mars all managed to gather their local material into finished worlds, given enough time and enough peace and quiet for gravity to do its slow, cumulative work. Jupiter's resonances make that kind of patient accumulation almost impossible across wide stretches of the belt sitting just beyond Mars. Long before any two small bodies could combine into something larger, Jupiter's steady, rhythmic tugging was already working to fling one or both of them away, or to stretch their orbits until any gentle, planet-building collision became a violent, destructive one instead, shattering material apart rather than welding it together over and over for as long as anything tried to settle there. Multiply that effect across dozens of resonant distances scattered through the entire belt, not just the 2 or 3 most obvious gaps that first caught Kirkwood's eye, and you arrive at an explanation for something far larger than a handful of empty lanes. You arrive at an explanation for why an entire planet never finished forming in this stretch of space at all. Not because the raw material was never there to begin with, but because Jupiter's gravity, patient and relentless in exactly the way a child's swing responds to a well-timed push, never allowed that material, the peace and quiet it needed, to actually come together. Picture the belt today, photographed from far above the plane where the planets travel, and those resonant lanes would still be visible as faint, thread-like gaps cut cleanly through an otherwise scattered field of drifting points. Thin, dark seams running through the belt at precise, predictable distances, an invisible signature of Jupiter's gravity written directly onto the architecture of the region, silent evidence of a process that never once required a single collision, a single explosion, or a single dramatic event of any kind to leave its mark. This is where the story Olbers told, and the story modern astronomers now tell, finally part ways for good, and it is worth being honest about exactly how they differ, because the difference matters more than it might first appear. Olbers looked at 2 small, oddly matched objects and reasoned backward to a single violent event, a planet that had existed and then been destroyed in one dramatic stroke. The resonance mechanism describes something almost the opposite, and unlike Olbers's original hypothesis, it did not have to remain a matter of reasonable guesswork for long. Later, astronomers, armed with far more precise tracking of asteroid orbits than Kirkwood himself ever had access to, ran the actual numbers forward using the known laws of gravity and watched, in careful computer simulations, as objects placed at these resonant distances behaved exactly as the theory predicted, their orbits stretching and destabilizing in a matter of a few million simulated years, while objects placed just outside those same distances remained calm and stable for the full length of the simulation. The mechanism was not simply a plausible story anymore. It was a prediction that could be tested, and it passed. Nothing here was ever destroyed in a single moment, because nothing here ever finished being built in the first place. There was no planet to shatter. There was only a patient, ongoing process of prevention, stretched out across many millions of years, rather than compressed into a single catastrophic instant, quietly working against any material that tried to settle down and grow. But Kirkwood's gaps, on their own, only explain part of the picture, and it is worth being equally honest about that gap in the explanation too. This reframing changes something important about how the belt itself deserves to be understood, and it is worth pausing on that shift before moving further. If the region is not a graveyard, then the objects drifting through it are not really wreckage in any meaningful sense either, whatever the old story called them. Wreckage implies something finished and then broken. What Ceres, Pallas, and every other asteroid actually represent is closer to raw material that never got the chance to be assembled in the first place, left essentially untouched since the solar system's earliest days, precisely because Jupiter never allowed it to be folded into anything larger, melted, reshaped, and erased the way material inside a finished planet eventually is. In that sense, studying an asteroid up close is less like sifting through a demolished building and more like opening a box of parts that was sealed and set aside before construction ever began, untouched by the melting, mixing, and reshaping that erases a planet's original ingredients almost as soon as it forms, a genuine time capsule from the solar system's infancy rather than a crime scene from its middle age. Resonances can clear out narrow lanes and discourage growth within them, but the belt's overall mass, the sheer, comprehensive thinness of the entire region, rather than just a few scattered stripes within it, called for something more. Modern research on how the early solar system actually took shape points to something considerably larger and more dramatic than Kirkwood's tidy gaps alone: the movements of Jupiter itself. In the solar system's earliest, most turbulent youth, long before the planets had settled into the stable, orderly orbits we see today. According to this picture, Jupiter did not form in the location we find it today and simply stay there. In the earliest few million years of the solar system's life, while the Sun was still surrounded by a thick disk of gas and dust, Jupiter formed relatively quickly, farther out from the Sun than its current position, and then began drifting inward, dragged along by its own gravitational tug-of-war with the surrounding gas disk. Some models suggest Jupiter migrated inward until it reached a point somewhere near 1.5 times the distance between the Earth and the Sun, deep into territory that would one day belong to Mars and the other inner, rocky planets, before Saturn's own growth and migration caught it in a kind of gravitational lock. The two giant planets briefly bound together by their mutual pull the way two dancers might lock arms mid-stride, and the pair reversed course together and began drifting back outward again, roughly retracing Jupiter's path toward the outer solar system before settling into something close to its current orbit. A journey spanning hundreds of millions of miles in each direction, carried out slowly over a span of perhaps a few 100,000 years, itself a mere eye blink against the age of the solar system as a whole. Astronomers who study this scenario have given it a fittingly nautical name, borrowed from the sailing maneuver where a ship crossing against the wind changes direction sharply and doubles back, the grand tack. The model was first laid out in detail in a paper published in the year 2011 by a research team that included Kevin Walsh and Alessandro Morbidelli, and it did not begin as an attempt to explain the asteroid belt at all. It began as an attempt to solve a completely different, long-standing puzzle: why Mars, of all the rocky inner planets, turned out so much smaller than Earth and Venus, barely a tenth of Earth's mass, despite orbiting in a region that older models suggested should have produced something considerably larger, when nothing about its position in the solar system obviously demanded that outcome. Planetary scientists had struggled with that mismatch for years, building increasingly elaborate models of the early solar system that could explain Earth and Venus perfectly well, but kept stubbornly producing a Mars 2 or 3 times heavier than the real one, no matter how the simulations were adjusted. The Grand TAC answered that question by showing that Jupiter's inward migration would have swept away much of the raw material in Mars's own neighborhood before it ever had the chance to grow into a larger world, cutting off its supply of building blocks early and leaving Mars permanently undersized, a kind of unfinished planet in its own right, stunted rather than destroyed, in a pattern that would turn out to look remarkably familiar once the same researchers turned their attention to the belt next door, where an even more extreme version of the same fate had apparently played out. Only afterward did researchers realize that the very same migration, sweeping through the neighboring asteroid belt on its way in and its way back out, offered a strikingly good explanation for that region's own strange, sparse population as well, tying 2 separate puzzles about the early solar system's uneven architecture back to a single shared cause. If this picture is correct, and a great deal of orbital and compositional evidence now supports it, then Jupiter did not gently disturb the region that would become the asteroid belt from a comfortable distance. It plowed directly through it, not once, but twice, first heading inward toward the Sun, and then again heading back outward toward its current home. Each pass would have scattered enormous amounts of material, like the wake behind a ship crossing open water, flinging smaller bodies onto wildly different orbits, some inward toward the Sun, some outward into the darker, colder reaches of the early solar system, and only a small, disorganized remnant left drifting back into anything resembling the belt's current location. The asteroids we observe today still carry a kind of fingerprint from that mixing, one that has nothing to do with a shattered planet and everything to do with 2 very different neighborhoods of the early solar system being stirred together by a single wandering giant. Astronomers divide most of them into 2 broad chemical families: drier, rockier bodies more common toward the inner edge of the belt, and darker, carbon-rich bodies, often carrying traces of ancient water-bearing minerals, more common toward the outer edge. Under the Grand TAC picture, this split makes immediate sense. The drier bodies represent material that started out closer to the Sun and was scattered outward by Jupiter's first inward pass, while the darker, water-rich bodies represent material that began much farther out in the cold neighborhood where Jupiter itself first formed and was carried inward during the second, outward-bound pass. A belt built from a single, local, shattered planet would never explain a divide this clean. A belt built from 2 distinct source regions, mixed together by one planet's long, looping journey through the middle of the solar system, explains it naturally. Researchers who model this process estimate that whatever mass originally occupied this stretch of space, the region now retains only a tiny fraction of it, potentially less than 1/1000th of what a fully formed planet would have required, scattered, ejected, and lost across the earliest, most chaotic million years of the solar system's entire history. Imagine a construction site where enough lumber, brick, and steel had been delivered to raise a proper house, and then, before a single wall could go up, nearly all of that material was hauled away again, piece by piece, over a period so brief in geological terms that it might as well have happened overnight, leaving behind only enough scrap lumber to build a small garden shed. Anyone arriving afterward and seeing only the shed, with no memory of the original delivery, might reasonably assume that a shed was all that had ever been intended. Only the delivery records, so to speak, the orbital and compositional evidence astronomers have since pieced together across 2 centuries of patient observation, reveal that something far larger had once been planned for that same plot of ground. And here the honest, unfinished nature of this science deserves its own moment, rather than being smoothed over into a tidier, more satisfying story than the evidence actually supports. Not every researcher agrees on exactly how much of that missing material was ever truly there to lose in the first place. Some models, including versions of the Grand Tack itself, treat the belt as having started out considerably more massive, closer to what would have been needed to eventually build a genuine planet, before Jupiter's 2 passes stripped nearly all of it away. Other, more recent studies, including work published in the mid-2010s by researchers such as Sean Raymond and Andre Isidoro, argue for a different picture entirely, one in which this stretch of space may never have held anywhere near a planet's worth of material to begin with, even before Jupiter ever moved an inch, its low mass baked in from the very beginning of the solar system's formation, rather than carved out afterward by any dramatic later event. Both pictures agree completely on the outcome sitting in front of us today: an overwhelmingly empty, sparsely populated ring of debris, nothing close to a planet. They simply disagree, honestly and without resolution, as of this telling, on how empty this region started out and how much of its original material, if any substantial amount ever existed at all, was actually lost along the way. Reputable scientists on both sides of that question continue testing their models against new observations, refining their simulations as better data comes in from surveys and spacecraft alike, comparing the precise compositions and orbital patterns their competing models predict against what telescopes and sample return missions actually find out there. And neither side has yet produced the kind of decisive evidence that would settle things for good. That kind of open, unresolved disagreement is not a weakness in the science. It is simply what an honest, active field of research looks like from the inside, long before any textbook has had the chance to settle on a single tidy answer. What both pictures agree on, and what neither one leaves any real room to doubt, is this: whatever happened here, it was not one comet striking one finished planet on one particular afternoon some unknowable number of years ago. It was not sudden, and it was not simple, and it did not leave behind 2 or 3 tidy fragments the way Olbers imagined when he looked at Ceres and Pallas, sharing an orbit that seemed, at the time, too specific to be coincidence. It was slow. It played out across millions of years, rather than a single afternoon, through the patient, repeated tug of resonances, and, quite possibly, through the wake of an entire giant planet sweeping through the neighborhood, not once but twice, rearranging everything in its path, long before any of the objects we now call asteroids had settled into the orbits they occupy today, which leaves Olbers's original insight in a stranger, more generous light than it has generally been given credit for. He was not a careless thinker chasing drama for its own sake, and given everything laid out here, he does not deserve to be remembered that way. He looked at 2 small star-like objects sharing an orbit where exactly one planet belonged, and he correctly sensed that something significant, something genuinely disruptive, had to be responsible. On that much, he was right, and modern astronomy has never actually contradicted him on this specific point. Something dramatic really did happen in this stretch of space. Enormous quantities of material really were scattered, ejected, and lost. A planet really did fail to exist where the old arithmetic once insisted one belonged. Olbers simply had the wrong drama in mind. He pictured a single sudden catastrophe, a comet striking a finished world, because that was the only kind of violence his era's physics had any vocabulary for. Working alone, with the instruments and the mathematics available to a Bremen physician in the earliest years of the 1800s, there was no way for him to have imagined a slower, quieter kind of violence, one measured out in millions of years and countless small gravitational nudges rather than a single collision on a single night. The actual drama was slower, stranger, and in its own way far larger than anything Olbers imagined. Not a world destroyed in an instant, but a world quietly, patiently prevented from ever being born at all, undone by forces that would take another century of mathematics and eventually a fleet of spacecraft to fully uncover. There is something almost tender in that correction, rather than anything dismissive. Olbers spent his nights doing exactly what a careful scientist is supposed to do, gathering the best evidence available to him, applying the best reasoning his era could offer, and following that reasoning honestly to wherever it led, even toward a conclusion as dramatic as a destroyed world, rather than shying away from a strange result simply because it was uncomfortable. He simply worked 2 centuries too early to have access to the one piece of the puzzle, Jupiter's own gravitational reach across time, that would have changed his answer without ever changing his basic instinct that something remarkable had occurred here. Science rarely punishes a careful thinker for reaching the wrong conclusion with the evidence available at the time. It simply waits, patiently, for someone else to arrive with better evidence. None of this, on its own, explains what all of that scattered, half-finished material actually looks like up close, or what studying it directly might still teach us about the earliest, most violent chapter of our solar system's history. Mathematics and computer models can only go so far in describing a time capsule. Eventually, someone has to actually open it. For that, the story has to leave the world of equations and orbital mechanics behind entirely, and follow the handful of spacecraft that have actually gone to look, settling into orbit around these leftover fragments, landing on some of them and bringing pieces of others home, turning a century and a half of careful mathematics into something that could finally be seen, touched, and measured directly, rather than merely calculated from a comfortable distance. One spacecraft had already proven, years earlier, before this story ever turned to Kirkwood's tables or Jupiter's long-ago wandering path through the inner solar system, that living among these fragments was nothing to fear. Spending the better part of a decade in quiet orbit around 2 of the belt's largest residents without a single close call, mapping their surfaces crater by crater and finding briny, salty secrets in the process. Results that reshaped how scientists think about water and chemistry, even in the smallest, coldest corners of the solar system. But an asteroid belt scattered across a region wider than the distance from the Sun to Mars is far too vast for one mission, however patient and however thorough its findings, to speak for the whole of it. 2 objects, however thoroughly studied, are still only 2 objects out of more than 1 million catalogued residents scattered across a region wide enough to swallow the orbit of an entire planet. A sample so small that generalizing from it alone would repeat, in a smaller way, exactly the kind of overreach Olbers once made from a sample of only 2 objects of his own. The next chapter of this story belongs to the spacecraft that came after, each one reaching farther and asking sharper questions than the last. Each one further proof that whatever danger, the old story once promised, had never actually existed anywhere along the way. A spacecraft named Lucy left Earth in October of 2021, carrying a name borrowed from an old and treasured discovery rather than from any Roman god or goddess, breaking with more than 2 centuries of tradition that had named nearly every object in this story, from Ceres to Pallas to Vesta to Psyche itself, after some figure out of ancient mythology. Decades before Lucy the spacecraft ever left the ground, paleontologists working in East Africa had uncovered the fossilized skeleton of an ancient human ancestor, roughly 3 million years old, a find so significant to understanding where our own species came from that researchers nicknamed her Lucy after a song playing on the radio the night of her discovery. NASA borrowed that name deliberately, just as the fossil Lucy offered a rare, direct window into the deep history of the human family. Mission planners hoped their spacecraft would offer an equally rare window into the deep history of the solar system itself by traveling out to study objects that have remained largely undisturbed since the very earliest days of its formation. Lucy's journey began, fittingly enough, with a detour directly through the region this entire story has been about, a chance to test its instruments against a real target before committing to the far longer, far more consequential encounters still years away. On the 1st of November 2023, the spacecraft passed close by a small main-belt asteroid named Dinkinesh, intended mostly as a brief instrument checkout before the real work farther out began, a modest rehearsal rather than a headline event. Dinkinesh delivered a surprise nobody on the mission team had been expecting. Tucked in close beside it, orbiting quietly, was a second, even smaller body, a tiny moon of its own, invisible from Earth and unknown until Lucy's cameras caught it in the frame during the approach. Astronomers later named the little companion Selam, after the same East African region where the original fossil Lucy had been found decades earlier, and after another, younger fossil discovered in that same region, a small child who lived and died long before recorded history began, tying the spacecraft's very first discovery back to the same human story that gave it its name in the first place, and offering a small, quiet reminder that even a routine checkout flyby through this supposedly empty region could still turn up something nobody had planned for or expected. Lucy's second stop came a year and a half later. On the 20th of April 2025, the spacecraft passed within roughly 600 miles of a second main belt asteroid, this one named Donald Johansen after one of the paleontologists who had helped uncover the original fossil skeleton decades earlier. The flyby revealed an oddly shaped little world, elongated and pinched near its middle like 2 lumps, loosely joined together, the apparent result of a violent collision that shattered a larger parent body somewhere around 130 million years ago, sending fragments scattering into what astronomers now call the Erigone family of asteroids, a scattered group of related fragments still sharing similar orbits today, drifting in loose formation the way a handful of leaves might scatter downstream from the same broken branch. The same kind of family resemblance among related debris that Kirkwood's own resonance work eventually helped explain on a much larger scale, decades before anyone imagined a spacecraft would ever fly close enough to photograph one of these family members directly, close enough to see the very shape of the ancient violence written into its surface. The results, published the following year in the peer-reviewed journal Science, gave mission scientists exactly what they had hoped for: confirmation that Lucy's instruments worked precisely as designed, tested and proven on a real target within the same crowded, well-studied stretch of the main belt. This entire documentary has spent its time explaining, well before the spacecraft would ever need them for the far more important encounters still ahead of it. Those more important encounters lie years in the future, out past the orbit of Jupiter itself, among a population of objects unlike anything found within the main belt this whole story has focused on so far. Sharing Jupiter's own orbit around the Sun, clustered in two great, loosely bound swarms trailing ahead of and behind the giant planet, drift thousands of asteroids known as Trojans, named after the warriors of ancient legend. Scientists studying these objects believe they may be some of the least disturbed material left over from the solar system's earliest, most chaotic years, primitive fragments that were captured into Jupiter's gravitational company rather than eventually forced into resonant lanes and flung away entirely, the way so much material within the main belt itself was. If the objects nearer to Mars represent a construction site that was interrupted early, the Trojans may represent something even rarer, original packaging that was never opened at all, tucked safely into a gravitational pocket where it has waited largely undisturbed for more than 4 billion years. Studying that untouched packaging directly is precisely why NASA committed to a mission as ambitious and as long as Lucy. No previous spacecraft had ever attempted to visit this many independently orbiting worlds in a single mission, and the engineering challenge alone, threading a single trajectory through 8 separate encounters spread across more than a decade, required a level of trajectory planning that would have been unthinkable in Olbers's era or even in Kirkwood's, when the very existence of an orbital resonance was still a fresh, barely accepted idea rather than a routine input into a spacecraft's flight computer. Each Trojan Lucy visits carries its own chemical fingerprint, its own surface composition, its own subtle clues about exactly which corner of the young solar system it originally formed in before drifting into Jupiter's gravitational company. Piece those fingerprints together across 8 separate targets, and researchers hope to reconstruct something no single object could ever reveal on its own: a detailed map of what raw material existed where and in what condition during the solar system's first few chaotic million years, filling in the earliest chapter of the same broader story. This documentary has spent its middle stretch explaining the same story that eventually produced both a finished Earth and an unfinished belt from the very same original cloud of dust. Lucy is scheduled to reach the first of these targets, an object named Eurybates, and its own small companion moon, in August of 2027, with 7 further encounters to follow through the year 2033, a single spacecraft visiting more independently orbiting worlds than any mission in the history of space exploration. While Lucy continues its long, patient cruise toward that first Trojan encounter, a second spacecraft is making its own crossing through the same general neighborhood, chasing an entirely different kind of mystery. Psyche launched in October of 2023, named for both the distant metal-rich asteroid it is traveling toward, and, before that, for the mortal woman of Greek legend who was granted a place among the gods. Its destination, an object also called Psyche, orbits within the main belt and appears, as best astronomers can tell from a distance using radar and careful measurements of its density, to be made overwhelmingly of metal rather than the rock and ice that make up most of its neighbors, a genuine oddity even among a population already full of oddities. One leading hypothesis holds that this strange little world may be the exposed metallic heart of a much larger body, a planetesimal that began forming early in the solar system's history, grew large enough to melt and separate into layers the way Earth itself once did, sinking its heaviest metals into a central core, and then had every one of its outer, rockier layers stripped away by a long series of ancient collisions, leaving only the dense metal core drifting alone through space ever since. Earth's own core, buried thousands of miles beneath the ground under your feet, formed through that same basic layering process billions of years ago, and remains sealed away forever beneath a thick mantle of rock that no drill or spacecraft will ever penetrate directly. If Psyche truly is a planetary core stripped bare, it offers something no experiment on Earth could ever provide: a chance to examine, directly and up close, the same kind of material that makes up the hidden heart of our own planet, without needing to dig through thousands of miles of solid rock to reach it. If that hypothesis holds up, Psyche represents yet another kind of interrupted world, a planet that had actually begun the slow, patient work of becoming something whole, only to be stripped back down to its most basic, essential ingredient before it could ever finish the job. On the 15th of May, 2026, Psyche completed a close flyby of Mars, using the planet's gravity to gain speed and bend its path onward toward the outer belt without spending a single drop of its own limited fuel. The lesson reaches further than our own solar system too, though the evidence for that wider reach comes from a different kind of instrument entirely. In recent decades, astronomers have confirmed thousands of planets orbiting other, distant stars, and in a growing number of those systems, telescopes have picked up faint, indirect signs of debris disks and scattered rings of rocky material. Systems with their own version of an interrupted construction site, tucked somewhere among their finished planets, detected not by any spacecraft flying through them directly, the way Lucy and Psyche fly through our own, but by the faint excess of infrared light such scattered material gives off when warmed by its distant star, a signal so subtle that only the most sensitive modern telescopes can tease it apart from the star's own overwhelming glare. Wherever a large, gas-rich giant planet forms early and close enough to a band of smaller, rockier material, the same basic physics that shaped the gap between Mars and Jupiter appears ready to repeat itself over and over in solar systems light years away that no spacecraft will ever visit directly. Our own asteroid belt, in that sense, is not a strange local exception tucked away in one otherwise ordinary solar system. It may be closer to a common, predictable outcome, one version of a pattern written into the physics of planet formation itself, repeating quietly across the galaxy wherever the right ingredients happen to end up in the wrong neighborhood, an unfinished sentence, written and rewritten, in slightly different words, around countless other stars we will likely never see up close. The movies were never going to tell you that version. A field of tumbling, dangerous wreckage makes for a better chase scene than an empty nursery ever could, and a shattered planet is a far more satisfying villain than an ordinary, patient law of gravity that simply never lets something finish. But the real story, once you sit with it long enough, asks for something the movies rarely bother to offer. Not excitement, but a kind of settled understanding, the particular, quiet satisfaction of finally seeing clearly what was actually out there all along. Once the wreckage and the danger and the century of inherited assumption are gently set aside, there is no chase scene waiting at the end of this story, and there never really was one. There is only a wide, quiet stretch of space between Mars and Jupiter, drifting along exactly as it has for 4.5 billion years, holding within it the patient, unfinished shape of a planet that gravity itself decided, gently and without malice, should never be allowed to close. Somewhere out there tonight, Lucy is still cruising toward its first Trojan encounter. Somewhere out there tonight, Psyche is still closing the distance toward a metal world that may turn out to be a planet's own naked heart. Neither spacecraft is in any real danger. Neither one ever truly was, not for one single moment of either journey. The danger was always ours, carried in our own imagination, inherited from a careful physician's honest best guess, and passed down generation after generation until a belt of harmless, scattered rubble became, somewhere along the way, a field you needed nerve and luck to survive. Sleep now, dreamer. The wide, quiet dark was never something to fear.